Coming to the next example. So this is for explaining decrement after addressing mode. Okay. This is the precondition. Assume these data in the memory. 80010 with value 1, C with A, and 8008 with value B, 8004 with value C. Okay. And the R0 register is used as a base address register with value as 80010. These are the initial contents of the registers R1, R2, and R3. The same data we have represented diagrammatically here. The memory map is shown here with these data stored in these memory locations. Okay, and R0 you can see it is pointing to this memory location 80010. If this instruction LDM DA R0 and not comma R1 to R3, if this instruction is executed, what happens is, since it is decrement after addressing mode used, so what happens is, first it's going to fetch the data from the address held in R0 and it will be transferred to which register. So now we are moving from higher address to lower address. Remember, whenever the pointer is moved from higher address to lower address, whatever the data that is fetched from the memory, it will be transferred to the higher register. So this is nowhere mentioned. Kindly note this. Okay. So if it is lower address to higher address, we are performing the operation. In that case, the data fetched from lower address will be stored in the lower register, and data fetched from next higher address will be stored in the next higher register in the list whatever you give in the instruction. Okay. But if it were to be the fetch operation from higher address to lower address, okay, it may be decrement after or decrement before addressing mode you are using. In that case, whatever the data you fetch from the memory, so that will be stored in the higher register. The next data fetched will be stored in the next lower register, and so on. So this is how LDM STM instructions will work. Okay. So if it were to be increment after or increment before instruction, it is the registers considered are from lower address to higher address. If you are using the addressing mode, decrement after or decrement before, in that case, the transfer will be from higher address to lower address. You need to see that it is from whatever the data fetched from higher address will be transferred to higher register. Okay, from higher to lower address, if it were to be, then higher register to lower register, the data transfer takes place. So this important point we need to know. The same thing happens in this example. Since it is decrement after addressing mode we have used, whatever the data that is fetched from the address held in R0, that data will be transferred to which register? It is R3 register. Okay, so it first transfer it into R3, and the pointer R0 will be decremented by 4. So it will be pointing to 800C. Next, it fetches the data at address 800C. That will be transferred to R2 register, and then it decrements the pointer R0. The next address held in R0 will be 8008. Okay, from this address the data is fetched, that is B. That will be transferred to R1 register. Okay, this is from higher address to lower address. The data transfer is taking place, and from higher register to lower register the data will be stored. So first data fetched is stored in R3, then R2, then R1. So whatever the order of the registers you give in this register list in the instruction, it will be from higher address, higher register to lower register, the data transfer that takes place. Okay, just observe the post condition, and what will be the final address held in R0 register. It is decrement after. Fetch the data, then decrement the pointer. Fetch the data, decrement. Fetch the data, then decrement. So what will be the final address? It will be 8004. Okay, 0004. So 0004. That will be the address held in R0 register. And observe the content of R1, R2, and R3 register. First data fetched, you can see it is in R3 register. The next data fetched is in R2 register. The last data fetched is in R1 register. So since we are fetching from higher address, so data fetched will be in the higher register than lower register. Okay. So same thing is represented diagrammatically here. After execution of LDM DA instruction, this is where R0 pointer will be pointing to. Okay, 80004. And you can see this is the next location. So the last data fetched is at address 80008, and the pointer will be pointing to the next location. Okay, after the last data is being fetched. Hope you can identify that. Okay, coming to the expressions to find the starting address and ending address. The addressing mode used is decrement after. Uh, that is what the description have given here. And you can see the starting address from that means the lower address. The starting address means it's from the memory block, the starting address or the lower address how actually you are computing, and what is the ending address or the higher address how actually you are going to compute. Starting address means it is not the location from where first data is fetched. Starting address meaning if you are having a block of memory, the lower address is termed as starting address in this prescribed textbook, and higher address it is taken as ending address. Okay, so how actually you can find out the starting address. So the lower address is here 8008. You can see these are the three locations that are fetched or that are accessed: 80010, 8000c, and 80008. These are the three locations which are accessed, where the lower address is 8008 and higher address is 80010h. Okay, this is the higher address. You can see the Rn minus 4 into n plus 4, where n is the number of registers used in the instruction. Totally 3 registers are used. So Rn is having the value 80010 minus 4 into 3 means it is 12. So 12 plus 4. Rn minus 12 plus 4. So what it results in? The lower address, that is 80008. Okay. And ending address, it is Rn. See, what is the data held in R0 register? It is 80010. That is the ending address. Higher address from where the data is fetched. So this is the block of memory from where the data is fetched into the registers R1, R2 and R3, where the lower address is 80008 and higher address is 80010. So whatever is there in Rn, that is the highest address from where the data is fetched, and Rn minus 4n plus 4, that is the address from where the data is fetched. That is the last data that is fetched from the lower address. And coming to the updation of Rn register, it is Rn minus 4 into n. Here in our example, Rn is having the value 80010 minus 4 into 3 means it is 12. 80010 means it is 16 in decimal. So 16 minus 12, what it results in? It is 4. 80004 is the final address held in R0 register. So this is how the register is updated. Okay, when you perform multiple register transfer by considering three registers R1 to R3. Okay, coming to the next addressing mode, that is DB, decrement before. As the name itself indicates, what do you mean by decrement before? Whatever the address held in R0 register, you just decrement first and then go for accessing the data. So again here, since this addressing mode, the access higher address first and then the lower address, whatever the data you fetch from the memory, the first data, that will be stored in the higher register. The next data fetched will be stored in the next lower register and so on. Okay. See, this is the memory status we have considered in the precondition, and same thing is represented diagrammatically here. 80010 is having the data 1, C is having the data A, 8 is having the data B, 4 is having the data C, and initial register contents are zeros. And this is the instruction that is executed: LDM DB R0 exclamatory comma R1 to R3. We have just replaced DA with DB addressing mode. Okay, once this instruction is executed, can you tell what will be the R0 register content and what will be the contents of R1, R2 and R3 registers? It is decrement before. What is the final content of R0 register? Yes. And what will be the contents of R1, R2 and R3 registers? Can anyone tell the contents of these registers? Are you all following? Yes? No answer?
R1, R2, R3 contents are A, B, C respectively.
R1, R2 and R3? Sure. What will be the R0 register content? R0
It will
final value.
0x8 304.
Correct. R0 register content is fine. What about R1, R2 and R3? Decrement, then 80010 is the data in R0. Once it is decremented, the address held in R0 will be 8000C. From
C.
this address, whatever the data fetched, it will be stored in which register? Is it R1? What I
R3.
explained this much.
R3, ma'am. R3.
R3. Kindly remember this. Data fetched from higher address will be stored in higher register. Next data fetched from the lower address will be stored in the next lower register, and so on. Nowhere it is explained in your book anywhere. So all this I've made an analysis. That's why I'm telling this information. You should not get confused. Whenever you are using increment after, increment before instruction, in that case, since we are moving from low increment after or increment before, means address anyway after performing the memory access or before performing the memory access, the address will be incremented. So whenever you are moving from lower address to higher address, the order in which registers are considered is lower register to higher register. So if you are using DA or DB addressing mode, in that case, you will be moving from higher address to lower address. So whatever the data that is fetched from higher address will be stored in the higher register. Kindly note this, okay? So in out of this R1, R2, R3, which is the higher register, it is R3 register. So first data fetched from the memory will be stored in R3, next data fetched will be stored in R2, and finally the last data fetched will be in R1 register. So what will be the content of R3? It will be A, content of R2 will be B, content of R1 will be C. That will be the result. Okay, see, R1 is having the value C, R2 is having value B, and R3 is having value A. This is bit confusing. Multiple register transfer is bit complicated compared to single register transfer. You need to remember the addressing modes IA, IB, DA, DB, and how actually each of these works. In both IA and IB, it is address will be incremented. Okay, whereas in DA, DB addressing modes, if you are using in the instruction, it is a decrement of the address held in the base address register. Okay. Just see the memory map after execution of LDM-DB instruction. R0 pointer, as you said, it is pointing to 800004, and this is the last location from where the data is fetched. This is the lowest address. The data fetched from the lowest address is stored in the lowest register in the register list. So here the lowest register is R1. Correct? So C is the data that is fetched from the lowest address 80004, and that data is stored in the R1 register. See, C is the data, you can see it is held in R1 register. Are you getting? This what is the starting address? It is 8004. Ending address from where the data is fetched, it is 8000C. Okay, this is the starting, and these are the three locations which are accessed to fetch the data. And you can see the expression here for decrement before. Starting address means the lowest address, it is Rn minus 4n. Rn minus 4n means it is what is the address? Okay, it is db, right? So 4 into 3 means it is 12. So 16 minus 12, what you'll get? It is 4. 8004 is the lowest address or the starting address, and ending address or the highest address for this memory access is Rn minus 4. What is 16? 10H means it is 16 in decimal. 16 minus 4 will result in 12. So 12 in hexadecimal, it is C. You should be familiar with hexadecimal representations. I performed internally decimal operation, and then I just represented the same in hexadecimal. So Rn is having the value, initially Rn is having the value 80010, which is 10H here. Minus 4 means it will be 12C. C in hexadecimal. That is the ending address. Okay. And what is the updation to Rn register after execution of LDM DB instruction? It is Rn minus 4n. 4 into 3, it is 12. So 80010 minus 12 C, if you say, the result will be 80004. This will be the final value in R0 register. So that is increment after or increment before. Final address in the base address register will be same. Similarly, whether it is decrement after or decrement before instruction, the final address held in the pointer register will be same. You can compare it with the previous value held in R0 register. But what is the difference you are finding here? In case of decrement after fetching the last data, the pointer will be pointing to the next location. Whereas here in decrement before, so the pointer will be pointing to the last location from where the data is fetched. We can see 80004 is the last location from where the data is fetched. Okay. Only difference you are finding is, since it is decrement before, first the address gets decremented and then it accesses the data. In case of decrement after, it accesses the data first from the current location held in the pointer, and then it is going to update the address. It decrements. Okay. So these are the 4 addressing modes supported in ARM with respect to multiple register transfers. So now coming to the applications of multiple register transfer. As I had listed the 3 applications. One is block transfer. If you want to copy the content of one memory block to another memory block, you can make use of multiple register transfer. One more application we listed is saving and restoring the context. So there's some register content you want to save and you want to perform some operations or using those registers, and then you want to restore back the register and pointer status. That can be done using multiple register transfer. And the last application is stack. The 2 applications we'll discuss in today's class. See, with the increment and decrement load multiple, this that is IA and IB, DA, DB addressing modes, we can go for accessing arrays in forward or backward direction. The content of the array can be accessed in the forward direction or in the reverse direction by using these addressing modes. And we can also make use of these instructions for stack, push, and pull operation. So in this prescribed textbook for pop operation, they are using the terminology pull operation. Okay. And coming to that, saving and restoring the context, what I told, the application of multiple register transfer. These are the register pairs you have to use for saving and restoring the context. It is not difficult to remember these register pairs, right? For the application, that is saving and restoring the context. For STM, for writing, for saving, we'll be using STM instruction. For retrieving the data from the memory, we'll be using LDM instruction. Hope you are aware of this. So store means writing to the memory, load means reading from the memory. So the instruction used with respect to multiple register transfer is STM and LDM. And followed by that, you are going to give the addressing mode. Just observe the register pairs here. If we are using STMIA, increment after addressing mode for store instruction. So what is the paired load instruction you have to use to fetch the data so that the context will be restored? It is DB. I you have to replace with D and A you have to replace with B. Okay. So in the next instruction you see IB you are having. You can easily tell what is the addressing mode with respect to load you have to use. Load multiple for that. See, I is replaced with D and B is replaced with A. So replacing I replaced with D. If we are having D, replace it with I, and A is replaced with B, and vice versa. Okay, this is the register, the instruction pair you have to consider for saving and restoring the context. So that with an example I'll illustrate. For the time being, just know the instruction pairs, load store multiple instruction pairs, which you can use for saving and restoring the context, right? So STMIA, the pair of the paired LDM instruction is LDMDB. STMIB, the paired instruction is LDMDA. STMDA paired instruction is LDMIB. STMDB, the paired instruction is LDMIA. Okay, it is easy to remember. Try to analyze here. IA, DB, IB, DA. We're replacing I with D and D with A. Similarly, A with B and B with A. If it is increment after instruction you are using, decrement before instruction for load multiple you have to use. If you are using increment before addressing mode for store, then decrement after instruction you have to use for load multiple. Similarly, for if you are using decrement after, make use of increment before addressing mode. If you are using decrement before for STM, then for LDM you have to use increment after. So one example for this instruction pair we'll see. Just observe this example. So if you use a store with base update, that means we are using not symbol, then the paired load instruction of the same number of registers will load the data and restore the base address pointer. That means context restoring can take place with these instruction pairs. Okay, so that's what is explained in that statement. Just observe the instructions and the preconditions here. See, R0 is having the address 9000H. R1, R2, R3 are having the data 9, 8, and 7. Okay, and we are using the instruction STMIB. If it is increment before, which is the paired LDM instruction, can you tell the paired LDM instruction to restore the context? Just now I told in the previous slide, which is the paired LDM instruction for STMIB to restore the context. Yes. Can anyone tell? I have to replace with what? Tell me the LDM instruction pair for STMIB.
LDM DA, ma'am.
Very good. LDM DA. I replace it with D. B you replace it with E. A before replace with after. Increment is replaced with decrement. So if you are using this instruction pair, you can save and restore the context. Okay, how actually it is done with the example you are seeing here. Just observe what is the R0 register content. It is 9000H, and R1, R2, R3 are having the data 9, 8, and 7 respectively. The instruction used is STMIB R0, R1 to R3. Three registers are being saved. Now we are trying to corrupt the data held in R1, R2, R3 register. We are trying to write some other data to these registers. Now we need to restore back the content of R1, R2, and R3. Okay, how actually it is done. So this is the precondition. Once STMIB instruction is executed, R0 pointer will be having the address 900C. Okay, since three write operations have taken place, R0 pointer will be incremented. So the final address held in R0 pointer will be 900C. You know that, right? If you are using IB, then what will be the final address in the pointer register? It is Rn plus 4 into n, where n is the number of registers. 4 into 3 means it is 12. So 900C will be the final address held in R0 register. And observe, now R1, R2, R3 contents are changed here. What was the earlier content in R1, R2, R3? It is 987. And we have saved these register contents in the memory using STMIB instruction. Now we are trying to corrupt the data stored in R1, R2, R3 by writing some move instructions. Now this is the post condition after execution of STMIB. Okay, we shall now execute the paired LDM instruction, LDM-DA, as you told. See, IB addressing mode for STM we have used, and here for LDM we have used DA addressing mode. If you execute this instruction, it restores the context. Restoring means the pointer register will get back the value 9000H, and R1, R2, R3 registers will get back the value 9, 8, and 7 respectively. Just observe the post condition, final post condition. See, the context has been restored. We had some data in the registers and the pointer register. We used STMIB to save its content. We corrupted the data, or we used the data, the registers to perform some other operation. And then we want to restore back that context. So that's why we have used the paired LDM instruction. And just observe the contents of R0, R1, R2, and R3. It is the same. We have restored back the context. Okay. So that you can see here in this memory map. After STMIB instruction is executed, R0 content is having 9003, and this is what the operation performed. 9000H is the address that is initially held in R0 register. Since it is increment before, what increment before addressing mode will do? R0 pointer will be first that is incremented. 9004 will be the address, and at this address R1 register content is saved. Correct? Increment before lower address to lower register to higher register, the data will be written. Remember, in general, IA, IB, if you are using it, moves from lower register to higher register. Since we will be moving from lower address to higher address. See, first address is updated to 9004. At this address, 9 data is stored, which is R1 register content. Next, the address is incremented, and then the data held in R2 register is saved. And again, the address is updated to 900C, where R3 register content is saved. Okay, this is what happens when STM-IB instruction is executed. Now, what we'll do is, we'll go for executing LDM-DA instruction. Once this instruction is executed, what happens? See, what is the final address held in R0? It is 900C. So first, at since it is decrement after, so 900C is having valid data. Correct? At this address, there is valid data. It is fetched. Decrement after means first fetch the data and transfer it to the register. So since it is higher address 900C, the data fetch will be stored in which register? 900C, whatever the data you fetch from 900C, it will be stored in which register? We are moving from higher address to lower address. Correct? To which register it will be stored? Decrement after is the addressing mode you are using for LDM. Okay. R0 pointer, you can observe it is initially having the address 900C. From this address, the data is fetched, which is 7. Whatever the data fetched, it will be transferred to which register? Out of R1, R2, R3. R3, getting? See, you can see the post condition. To R3 register, it is transferred. Next, the address gets decremented. Now, the new address will be, updated address will be 9008. The data is fetched. It will be transferred to R2 register. Next, the address gets decremented. It will be 9004. From where the data is fetched, that is 9. It will be transferred to R1 register, and then address gets decremented. So what will be the final address? It is 9000. You can observe for STM-IB, the instruction pair you need to consider, it is LDM DA. So using this register pair, you can save and restore the context. So any of those instruction pairs you can consider. If you are using STM, that is the IA instruction, then you have to use DB. STM DA instruction if you are using, then in that case IB instruction you have to use, and STM DB if you are using, then in that case IA is the addressing mode you have to use with respect to LDM instruction. Okay, so this let me illustrate with the example. One more example you can observe. Let me store. Let me take the address. So LDR, I'll consider R0 comma equals. So some location I'll consider, and now I'll take the register contents R1, R2, and R3. R1 with move R1 comma hash. I'll use 0x01, and I'll take some data in R2 register. These registers contents I want to save, and then I want to restore back these register contents. R2 register, I'll take it as 02, and I'll take R3 register as 03, 0x hash 0x03. So what I have done here is I have stored the address of the location, okay, where the data is to be saved in the R0 register, and R1, R2, R3 are the registers which I want, whose content I want to save in the memory. This is the data held in R1, R2, R3, 1, 2, and 3 respectively. Now I'll use STM instruction, okay, STM IB I'll use, IA I'll use, STMIA, that is increment after, okay, R0, I'll use the pointer, R0 as the pointer, R0 comma, I'll use the register pair as R1 to R3, okay, this is what the register pair I use. Now, it gets saved. So once STMIA instructions executed, R1, R2, R3 contents will be saved to the memory starting at address held in R0 register, which is the base address register. Now I'll corrupt the data held in R1, R2, R3 register. I'll write some data, move R1, comma, hash 0x10 and keep, move R2, comma, hash 0x20 and keep, and move R3, comma, hash and keep 0x30. I've corrupted the data held in these registers. Now I want to restore back the context. So what is the pair of LDM instruction I have to use? LDM. Okay. IA has to be replaced with DB. Decrement before R0, comma. I'll use the same register pair. I have to use the same register pair for restoring the context. You cannot use some other register. It will not restore the context. For saving and restoring the context, this is the register pair. Instruction pair you have to use. STMIA if you are using. In that case, LDM. DB is the register pair you have to make use of. Now, let me write an infinite loop. Right. Stop label and key. And I'll use the instruction branch to stop. Now let me give the data segment area ex2 comma data read, right? Now let me locate some memory where the data is to be written. Location, I'll use DCD space. I'll use some memory block. Okay. End. Hope the instructions are clear. Let us just assemble it and execute. Okay. I'll start the debug session. Now you observe the data in the registers. Okay. See, first instruction is executed. LDR R0, comma equals location. This is the location where the data will be saved. So that is 4 followed by 70H. And now R1, R2, R3 are initialized with this data 1, 2, 3. Now we are saving these register contents to the memory. STMIA increment after. So first data, whatever you are having in R1 register, that will be stored at address 4 followed by 70. The next address will be stored in the next word location. Okay, and so on. See, STM IA instruction is completed its execution, and you can observe R1, R2, R3 register contents are saved in the memory. 4 followed by 70H. At this location, R1 content is written in little endian format. In next 4-byte location, it is R2 content written. In the next 4-byte location, R3 content is written. So if you are moving from lower address to higher address, from lower register to higher register, the data will be written. Okay, 1, 2, 3 is the data held in R1, R2, and R3 respectively. Now we are corrupting the data held in R1, R2, R3. See, we are writing some other data in R1, R2, R3, 10, 20, 30. I want to restore back the status. Okay, whatever the status we had in the pointer register as well as in the other registers R1, R2, R3, I need to restore back the context. So LDM DB is the paired instruction we are going to execute. Once this is a DB means decrement before. Okay, first data that is fetched. The address is 4 first followed by 60C. This is the address held in the base address register. So that is the data where that is the location after 3 to the next location it is pointing to. So it decrement before means now the pointer will be pointing to the data that is 3. Okay, so see, first data fetch will be transferred to R3, then R2, then R1, since it is decrement before addressing mode you are using. Just observe, as soon as I execute this instruction, these three word data is fetched, 32-bit data is fetched, and it is transferred to R3, R2, and R1 respectively. We are moving in the reverse direction from higher address to lower address. The first data fetched from the higher address, it has been transferred to R3 register. The next data fetched from the lower address is transferred to R2 register, and the data fetched from the least significant address, that is 4 followed by 70, that data is transferred to which register? It is R1 register. So this is how you can save and restore the context. Okay, so any order you give, the registers, if you are either giving as say R3, I'll give it as R3 comma R2 comma R1. I'll give in this order. Whatever the order you give in the register list here. So if it were to be IA addressing mode you are using, then first it is going to save R1 content, then it will save R2 content, and then it will save R3 content. So from lower address to higher address, if you are moving from lower register to higher register, the data will be taken. Is this clear? Have you all followed? Yes or no?
Yes, ma'am.
Okay. Moving on to one more application of the load store multiple instruction. So this is the problem. Copy block of 32 bytes from source address location to a destination address location. So some block of memory you are having, from that you need to fetch the data, and that is 32 bytes of data from one block you have to fetch and you have to transfer to another block. So the starting address of the block will specify. For that we require the pointer register. Here we are using in our implementation R9 as a register for fetching the source data. The address we are assuming address held in R9 as 8000H. R10 is a pointer to write the data to the destination block. We are assuming the address as say 9000H. So I have considered these addresses to just to show you the memory map. Okay, how actually the block transfer takes place. And if you are using block transfer, the same addressing mode you have to use for STM and LDM. Okay, store multiple for and load multiple for these instructions. You need to use the same addressing mode. If you are using IA for store, you have to use IA for load also. Okay, whatever the addressing mode you are using, the same addressing mode you have to use if you are using the if you are considering the application block transfer. If you are going for saving and restoring the content, that application, in that case it is vice versa addressing modes you need to consider. IA if you are using for STM, in that case you need to make use of DB addressing mode. Hope you are getting. So for this application it is the same addressing mode you have to use. So LDMIA, this is the instruction we are using for fetching the data from the source block. LDMIA R9 not, comma R0 to R7. Since it is 32 bytes of data we need to fetch, we require 8 registers in the register list. R0 through R7 we are using. Totally 8 register. Each register is of 4 byte. Okay, 8 into 4 it is 32. Getting? And the equivalent instruction, that means an instruction to write the data to the destination block, it is STM, and we'll be using STM IA addressing mode only. How actually it works we'll see. Before that we will see the memory map after execution of LDM IA instruction. See, 8000H is the starting address, and we are trying to write this is fetching the data LDMIA. We are fetching the data starting from address. It is 8000H. Each data fetch is transferred to the registers R0 to R7 respectively. Just observe, this is increment after addressing mode use. First, it fetches the data from address held in R9. What is the address held in R9 register? It is 8000H. What is the first data fetch? It is 10H. It is retrieved and it is returned to R0 register. Then address gets incremented. This is increment after addressing mode use. Then 8004, from this location data is fetched. It is returned to R1 register. Next increment 8008, the data fetch is transferred to R2 and so on. Okay, after fetching the first 8 location data, pointer will be updated. Since it is increment after, it will be pointing the next location. If you see R9 content after execution, it will be 8020. If starting address held in R0 is 8000, the ending address will be 8020. Okay, so now we'll write STMIA instruction. These are the only two instructions you're using to perform this operation. Copying 32 bytes of data from the source block whose starting address is 8000H to the destination block whose starting address is 9000H. The STMIA R10 not, comma R0 to R7. Same set of registers you have to use and same addressing mode we have used, IA. Okay. See, after execution of STMIA instruction, just observe R10 pointer is pointing to the address 9020. So what happens? This is store instruction. That means whatever the data held in the registers that we are writing to the memory. So since it is increment after, what happens is it's from lower register to higher register, the data will be accessed. See, R not register content is taken, it will be written to the address 9000 head, then the address gets incremented to 9000, that is 9004. Then R2, R1 content is taken, it is returned to this location, pointer gets updated to 9008, where R2 register content is written, next pointer gets updated, R3 content is written, and so on. Finally, R10 register content will be 9020. So this is how we can go for block transfer. If you want to transfer the data in one block to another block, you can use the instructions LDMIA to fetch the data from the source block, and STM instruction can be used to write the data to the destination block. You have to use not symbol, and you need to specify the base address registers which holds the starting address of each of the block, and you can observe the addressing mode we have used in each of these LDM and STM instructions. It is IA only. These are the two applications we have discussed in today's class. One is saving and restoring the context using LDM and STM instruction pair. You need to know the instruction pairs to be used based on the addressing mode. You can easily remember those instruction pairs for performing that saving and restoring the context. And another application is transferring the content of one block to another block. Okay. So that's what I listed here. In this both store and load multiple instruction, they are using the same addressing mode, that is increment factor.